Not going to repeat my sum joke. It was in the moment. Just no, it just needs to come when it does. So we are learning to insert learning objective. We'll be successful when we can insert learning outcome. Hey, those are words. Indefinite integration. That's when we wrote a function like this and like, hey, what's its antiderivative? Well, its antiderivative of f of x is capital F of x. And then we always put a plus c with it. So like the antiderivative of, for instance, like x squared is 1/3 x cubed plus c. Because when you take the derivative of 1/3 x cubed, multiply by 3, subtract 1 from the exponent, you get x squared. So that's indefinite integration. That's what we did in lesson 4.1. Definite integration looked like this and was saying, well, let's find the area under f of x from the x values a to b. So like this is exactly equal to the area S when it represents that exact area. And we talked about approximating that if it wasn't a geometric thing. Like this one, we would just approximate by using a bunch of rectangles. Yeah, that's basically what we would do. We never related these two things. They look like maybe we should relate them, but they are different, right? Like there's a lot of times we use the same symbols or same words in math or just language. They look similar, but are completely different things. Completely separate. Like it seems silly to try to force a connection if there really isn't. Just because we use the same symbol doesn't mean it means the same thing or that they're even remotely connected. This is clearly just like a hoax perpetrated by yours truly to try to make you think that there's more to this than there really is. Because hoax has been a giant word this past like 6 months. So, but anyways, it's clearly a hoax. I'm clearly setting you up for a hoax. And we're going to go down the conspiracy theory thing and just completely rattle your brains full of shit. Oh, I'm recording. That's probably bad. Whatever. So there's probably nothing there. It's a hoax. There's probably nothing there, right? Did you see that? I thought I saw something. Did you see that? Ah! There it is again. Get her, get it. Well, that kind of escalated quickly. So, those troll faces, they are leading me to believe that this is not a hoax, that there might be something. So, indefinite integration and definite integration must be connected. But how? How are they connected? Hey, listen. Navi's got an idea for us. I'm not really sure what her idea is. She just says that all the time. Usually it's not helpful. Maybe it's helpful this time. She found something. Maybe that's helpful. What does FTOC stand for? FTOC? Where's that? Oh, bright pink arrow. That's right. FTOC. 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 Well, O is small, so it's probably a helper word. Fundamental theorem of calculus. Seems fun. Just waiting for the boos.
Did you not see me? I slapped my knee.
I saw that. I did see that. I was just waiting for someone to just go boo. I just needed at least one boo. Thank you so much. I needed that very much. I need the knee slapper, but the boos is really what I'm looking for. Awesome. Yes. All right. So before we actually find out what the fundamental theorem of calculus is, you need to know this, young Padawans. It's fundamental because it connects integration to derivatives, indefinite integrals to definite integrals. So what the hell is it? All right. Let's warm up and start fusing some things together. So here's the indefinite integration. Here's our definite integration. Let's fuse these sun guns together and get something. It's a fusion dance from Dragon Ball Z, if you don't know. Uncultured swine. There. Bam. This right down here is the fundamental theorem of calculus. So good. Oh my God. I almost cried. Like, I'm going to watch it again and definitely just like cry and bawl. I did watch the new Mando episode. Oh my. Woke up early for it just in case.
Watch what?
The newest Mandalorian episode. I woke up early just to watch it before school today. Because I'm like, just got to make sure. It's not even oh my, we're going to talk about this in just a little bit. I am going to keep messaging you as I'm talking.
Do you have the vid?
No. My coffee, when I make it, I use a reusable filter, which is built in it, and it usually leaves some particulate at the bottom. And sometimes when I drink, I don't mix it back together well enough. And that's just a product of reusable filters. Yeah, so sometimes if I don't mix it together, like sometimes when you see me swirling, it's not just because I like the aesthetic. It's because I'm just making sure that it all goes back in there and it's slightly chunkier. So I don't get all the particulate at the same time. But then again, if I just chug the rest of the bottle or the cup, I'm still getting the rest of the particulate anyway. So I mean, So this is the fundamental theorem of calculus. What this says is I can evaluate a definite integral by finding the antiderivative of the function and then finding the difference of the endpoints when I plug them into the antiderivative. That's what the fundamental theorem of calculus says. So let me show you two and verify. I got to animate the slide a little bit better so it goes at once. So why don't you take like just 10 seconds to look at those and see and get your own reactions, and then I'll talk about them more. That's one of the bounds. Yeah, the bounds might be hard to see. I got to remake this slide and these problems. But what this says is the integral from 2 to 5 of x squared dx. So using fundamental theorem calculus, what I'm going to do is I'm going to take the antiderivative of x squared, which is 1/3 x to the third plus c. Now I'm putting plus c in here only for this one, and you'll see why. Again, this is the antiderivative. I can check that I did the correct antiderivative by doing the derivative of 1/3 x cubed. Well, I'll bring the 3 down. 1/3 times 3 is 1. 3 minus 1 is 2, so I get x squared, which is the original thing. Okay, good. That's the correct antiderivative. And the derivative of c would just be 0. Now what I'm going to do is I'm going to plug in 5 and 2 to the antiderivative and find the difference. And now that I plugged them in, I'm going to find the difference. Boom. And I get 39. Just to make sure that you don't think I'm just fooling around with you. And I know how much you trust Desmos. I mean, I trust Desmos quite a bit. Let's see what Desmos has to say. Yeah. I mean, if you go plug it in the calculator.
Hey, stop talking about the Mandalorian.
Shh. All right, fine. Okay, but so that's that one. Notice how there's a plus C and a plus C here. It's plus C minus a plus C. The C goes away. It doesn't really matter when you're coming into the evaluation. So when you're doing evaluate indefinite integral using the fundamental theorem of calculus, you don't need to put the plus C here. This is extra because it just goes away anyways. You technically can put it in there. That's fine, but it should always disappear when you're using it this way. Here's another one. This is just x to the 1/2, which is also the square root of x. Antiderivative of that, again, add 1 to the exponent, then multiply by the reciprocal. So what? 2/3 x to the 3/2. Take the derivative of that. You'll see that should be the antiderivative. Now let's plug in 4 and 1. Plug in 4 and 1. Boom, 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 boom. Should be 14/3 is the exact area of this one. Again, Desmos, what say you? Says it's 14/3. Seems legit. But it's still like, wow, really? Like all that approximation with rectangles and stuff builds to this. That's it. Oh, wait, there's more. Fun fact, Billy Mays never said this in a commercial. He's never been on record saying, but wait, there's more. But we always think he did. So it's always interesting. Anyways, and then there's this. This is sometimes called the second fundamental theorem of calculus. I like to think of it as just a consequence of the fundamental theorem of calculus, or just part 2, whatever you want to say. Basically, there's a lot going on here. Here's the interpretation that I want you to take out of this. What this means is that integration and differentiation are inverse operations. So whether it's indefinite integration where you just find the antiderivative, or definite integrals where indefinite integration where you're finding area under a function, integration, differentiation are inverse operations. They undo each other. The second one, by the way, notice how it's derivative in terms of x, but there's a u here. Sometimes you're going to have to deal with chain rule doing stuff like this. And I just want to point this out. We'll deal some more with this later, but I just want you to see this now. So, but why this? Why does this work? Like, I'm telling you it is, but why is it a thing? The proof of this was pretty quick, so I wanted to show you. Well, using what we just talked about, we can do this. Using the fundamental theorem of calculus, we can rewrite this piece. So the antiderivative of f of t is capital F of t. So I'm going to plug in x and a and find the difference between those. Boom. Now I want to take the derivative of this. And in order to take the derivative of that, I can take the derivative of each piece separately. Well, the derivative of capital F of x is just regular f of x. But what about this piece? What happens here? Well, that's f of a is just a number. A, B, C, those letters at the beginning of the alphabet are pretty much always assumed to be constants. So f of a, that's just going to be some number. The derivative of some number, the derivative of a constant, is just 0. So that's why that works. And again, you can do the exact same thing for this one down here. Okay? Again, the letters at the end of the alphabet are assumed to be functions or variables. And we let u be a variable often. So you could do the exact same process to see why this should be true. Okay? So there are the two parts side by side. Again, this is technically like fundamental theorem of calculus part 1, or the first fundamental theorem of calculus. This is fundamental theorem of calculus part 2, or the second fundamental theorem of calculus. They're both part of the same thing. Different people talk about them different ways. Different books talk about them different ways. You can search the internet and I'm not even sure there's a heated debate about it, but there's just differences in opinion about that. No worries. I appreciate the change of scenery. And I'm still going to wait to respond to the other thing, but I just got called out. But wait, there's more. The two more things I want to show you. There's a kind of a meaty lesson. This first one, this is a number. Like this is the area between these two numbers under this function. The second one is a function because it's the area from A to whatever X is. Okay. The idea is the second one is what is referred to as accumulation function. The AP test calls those accumulation functions. Several books other than our book calls them accumulation functions. So that's something I want to just point out to you. And here's the animated GIF showing you how, as X changes, how the area changes. Again, it accumulates area as X gets bigger than A. Again, you can watch and see how the area changes. Right here, this line right here, F of B, is saying like, what happens when we let X be different numbers? Well, if we let B just change, and if you look closely, there's an X there. It's, what's the word I'm looking for? It changes over time. You can see what the total area is equal to as it changes. Again, in the GIF, B equals X. Here's two different ones. This is the one I just showed you, and here's one with just like a polynomial function. So I just wanted to throw some more at you so you could see two different accumulation functions like actively moving. I think there's something fun about that. Also, I just found out that Screencastify can make GIFs. So you're probably going to see more of those from me. Pre-calc definitely is. I'm pretty sure I'm going to have you all too. I got to also work on animating this slide. There's just a lot to throw at you all at once looking at this. But average value of a function is another thing that this consequently gives us. So this rectangle, I'd say, has an area of 100 and has a width of 5. So what should its height be? Well, it should be 20. And you get that by taking the area and dividing by the width, and it gives you a height. Now, a rectangle has a constant height. But what if you have something that doesn't have a constant height? You take the area of something that doesn't have a constant height and divide it by the width, you get an average height. Or if it's a function, an average value of that function. So if this right here, this is an expression for average value of a function. If you take the area of the function and divide it by the width of the interval, you get the average value of the function. Okay. What that means is that this green area is exactly equal to this gray area, the black area. And this horizontal line here is the average value of the function on that interval. Here's the setup to what's going on in the animated GIF when you get around to it. You can spend some time looking at it, but basically G of t is just the average value of the function. And the integral from a to b of G of t is the area underneath it, so the area of a rectangle. And this is just the area of the function. And you notice here as b changes, the area under the average value and the area of the function are exactly the same. But then the average value, you can see the horizontal line, changes the further we go to the right. That's it.
Do you want to joke now?
I do. Oh, I have one more thing I want to say, then yes. So there's that. We're probably going to just kind of keep moving after break. We may spend another day after break. I don't know yet. We'll see. But the big thing I want to tell you is it looks like a lot, and quantity-wise is a lot. Just start see where you can get, try a couple. Make sure to read the section because there's a lot here. It's a meaty section. It due soon. It's due after break. It's not due until probably that Friday. It looks like so many. They'll go quicker than you think. Okay, joke.
What did the Zen Buddhist ask the hot dog vendor?
Do you have one with everything?
That's pert near the actual answer. Make me one with everything.
Oh, so close. Yes.
All right, so I recently had purchased a beehive so that I can raise my own bees and make my own honey and all that jazz. And so I was going to the bee store to buy bees for my beehive, and I asked for 12, but when I looked in my bag, there was 13, and I said to the owner, "I have 13," and he goes, "Oh yeah, that's a freebie."
Well played. Well played.
Yeah. Why did the tectonic plate split?
They were on a break.
No, there was too much friction between them.
Well played.
Yeah.
I like those jokes.
Okay, that's
So-
all I got for now.
That's all you got? That's fine. My
I'll
jokes.
replenish the joke supply over break. Don't worry.
Oh, ooh, yes. You have plenty of time for to sit, stew, think about those things. Oh, before anyone leaves, I have one more thing I want to say. I hope you have a nice break. I hope you can find some way for it to be restorative. I hope that you don't have tons of things to do over break. I hope you get to choose the activities and things that you get to do and people to hopefully see virtually. Yeah, I hope you can find a way for it to be restorative. I'm not going to say I hope you have a great break. I hope you find a way for it to be restorative. Like I'm really trying not to give you a whole lot to add to that stress. I know I just literally gave you like 75 problems, but AKA not doing the math homework. But you may just want to look at it once or twice and then maybe start working on it the Monday after break. I don't care. As long as you got the quiz done before you go on break, that's really what I care about. And I think there's one of you that needs to finish that up. So if you could please finish that quiz before break, that would be super duper so that I don't have to holler or so we don't have to think about it basically and just finish it today. It'll be all right. That's all I have for you today. So on that note, have a wonderful day, folks. I hope you have, again, a restorative break in whatever capacity you can find it. And we'll see you next year.
I hope you have a great break too, Mr. Last.
Thanks. I'm hoping so. We'll see how it all goes.
See you next year.
Ah.